You made evolutionary one appendage, and you duplicate it, and then you modify those appendages. All right? So that's metamerism. We've gone over coelom. Cephalization is the clumping of neurons in one end. These have radial symmetry, so no one part of the organism enters a new environment relative to the other. But if you think about a bilaterally symmetrical organism like the flatworm, we'll be looking at one. So if it moved in this direction, what part of the organism, A, B, C, or D, it moves in the direction of B, what part of the organism would enter the environment first? B. So in fact, we find cephalization here, where we increase neurons at one end, it's the anterior end, direction of movement, and that's things like vision. It might just be how much light you can detect, etc. There's coordination of movement, etc. There might be smell, taste, various things like that, and we get clumping in there. Because you want to test the new environment, is it safe to be entering? Okay. So that's what cephalization is, and then I think everything else is pretty much straightforward. There always is a question about what respiratory pigment means. If gases are transported bound to a molecule, we would say that's a respiratory molecule or protein for transport. They're almost always colored, like hemoglobin or hemocyanin in that. So generically, we call those proteins that bind gases respiratory pigments, okay? Because they usually are colored. Right? So by respiratory pigment, we can mean hemoglobin, hemocyanin, and you know that your hemoglobin is bright red when it's oxygenated, right? And what color are your veins? Blue, because they're deoxygenated. So typically, if you cut the surface of your skin, that's going to be from a vein, or venule, maybe a capillary that's deoxygenated. If you really, I've never done this, but I'm sure it's true. If I took my arm and put it in an oxygen-free environment and I cut a vein, I'd bleed blue. It wouldn't turn red. The reason why it turns red now is because it's exposed to outside air, right? So you do get this change in the color. All right. Anyway, in terms of body plans, we talked about the polyp versus medusa. And if you think about jellyfish, remember there's this extracellular matrix between the two layers. In jellyfish, this extracellular matrix is pretty thick and jelly-like. The basis of the term jellyfish. In terms of the hydra, that extracellular matrix called mesoglea is actually pretty thin. So you'll have a tough time seeing it. You'll definitely see the gastrodermis in yellow, and you'll definitely see the epidermis or ectoderm here in the outer blue, okay? All right. Here just illustrates some examples of these. Here's the hydrozoans here, the scyphozoans, the jellies. Here's the cubozoans, the box jellyfish or sea wasps. They actually have these eyes around the perimeter here. It does not, we're not sure if it forms images. They're rather complex, grouping of eyes, things like that. There's some research being done now, because these things have, what's unique to this phylum is a cell type called a cnidocyte. So that's unique to this phylum. It's the only phylum that makes this cell type, and it's called a cnidocyte, basis of the term cnidarians. Cnidocyte. That's the cell. They have an organelle within there called a somatocyst, which is a stinging organelle. They can have toxins with it, etc. So when you get stung by a jellyfish or a sea wasp, which is a common name for the box jellies, the venom's being injected, okay? And this can be a real problem in certain parts of the world, especially off the coast of Australia. So some researchers are studying this, and they've determined that they actually avoid the color red. So they're thinking about putting at beaches red netting, so that when these sea wasps get close to the shore and they see the red nets, they will be basically afraid of the red nets and not enter the beaches. They haven't tried it yet, but that's one area of research. And then, of course, the anemone here, and we'll see this in the marine tank. We'll have the GSI demonstrate this, or the UGSI. We won't do lots of people, but if they stick their finger in the aquarium and they go near one of these tentacles, these cnidocytes are throughout the body, but mostly on the tentacles. If they stick it near a tentacle, it will eject those nematocysts into the finger. Now, they're not going to scream out in pain because these aren't lots of toxins in these. Actually, the skin's very thick, so these things aren't. These things, the ones we have are not venomous, so we don't have to worry too much about them. But what will happen is, if they move their finger slightly, you'll see the tentacle be pulled because that cnidocyte has discharged nematocyst and it's stuck in there, okay? And one semester, I never feel it with my fingers, so one semester people asked me, so I stuck my tongue down there because your tongue's a little bit more sensitive, and yes, I did feel it. It didn't really go numb, though, but it's a lot more sensitive. So anyway, here shows you the hydra. A couple illustrations here. We have two forms of reproduction occurring here. As a biologist, you have to do something sometimes, okay? Anyway, here's the gastrovascular cavity here. We can't tell it in the whole organism, but there's a cavity within there. Notice we have a bud forming here, illustrated here as well. Here you can see that cavity clearly. These are genetically identical, so this is an illustration of asexual reproduction. But they can also have testes and ovaries where we produce sperm and eggs. The sperm are released. Usually you promote cross-fertilization, so there's some self-incompatibility sometimes, so certain proteins won't allow the same organism to fertilize itself. And then the eggs get fertilized here, and then we produce a zygote, and then it would be released. Anyway, a few things to point out. Here's the gastroderm here. You see flagella here. They help to create a current, distribute these nutrients, the fluid in there. When they feed, they coordinate the tentacles, and they capture the food, and then they'll ingest it through the mouth/anus. It'll be in here. So various cells will develop digestive enzymes out here, like this gastrodermal gland cell. Develop digestive enzymes out. You start getting extracellular digestion. And you'll see that these organisms they feed on are quite large. So in lab, what you'll be doing for the cnidarians, because it's kind of hard sometimes to keep track of everything you have to do in lab. For the sponges, it's just looking at them. For the cnidarians, so for the periphery, basically demos. We'll have demos of everything, demos. But you're going to do a feeding behavior. So you're going to look at feeding on them, and you're going to look at some slides for this, okay? So you'll watch them feed. You'll see those tentacles. You won't see the nematocysts discharge because they're below the resolution of your microscope, so you won't be able to see that. But you know what's happened. And this illustrates close up with this. So some slides you look at, you'll see the mesoglea, this thin layer here. There's those cnidocytes with the nematocysts. Here just shows you one of those cells that we release digestive enzymes. Here shows you not only do we have extracellular digestion, we also have intracellular digestion. Get this food vacuole formed, okay? So the three layers: gastroderm, epidermis, and the mesoglea. Okay? Any questions? So you'll look at both cross sections and longitudinal sections there, and do the feeding demo. For the platyhelminthes, the three groups we'll look at: the turbellaria, the trematoda, and cestoda. The turbellarians are the free-living forms. The trematodes are the flukes. Some people say liver flukes, but they can infect other tissue besides just the liver. And the cestoda, which typically are in the GI tract. Okay. And so what we've done now is we're on this branch of the triploblasts, and we can also say these are all. So now we're going to go to the protostome branch. And deuterostome was last week with the chordates. So now we're on the protostomes. And this will be helpful if you try to organize your study notes like this. So protostomia, we're doing platyhelminthes, and we have three groups within here. We have the turbellarians, we have the cestoda, and the trematoda. Okay? And then this, of course, is platyhelminthes. So let me just, again, here's the chart. The answers are here. You can just copy them down if you want. But realistically, if you want to do well, you'll try to come up with the answers for yourself. It takes some time to do that, but it's going to be a learning experience. So again, we don't have a coelom here, but they are indeed in the protostomes. Okay? And then metamerism is a little bit internal. We'll see that. Some cephalization. We do have eye spots. They are not image-forming. In the turbularians, they're not image-forming, but they do detect light. So when you're in lab, this is the one time you shouldn't use an illuminator, because they'll want to always keep swimming away from it, okay? Usually you do want to use an illuminator. Anyway, no surface resistance, no rest resistance. These things are flat. That's why they're called the flatworms. So the distance to diffuse gases, et cetera, is pretty small, okay? And as a result, it's not a rate-limiting aspect. How many of you are interested in public health medicine? There's tremendous import about, platyhelminthes in particular because of the various diseases the trematodes or the cestodes can cause. This just shows you, for the trematodes, it's usually, they have two hosts within the life cycle. They usually have a vertebrate, or in this case, we're focused on humans, a vertebrate, and then an invertebrate form, and oftentimes it's snails. And the key issue of this is, you have this infected human releasing feces into the water, which then you get these larvae, and the larvae infect the snails. Okay? And then the larvae penetrate the skin here, and that completes the life cycle. And this just shows you a male one here and a female mating for sexual reproduction. Then this just illustrates to you tapeworm. If you eat food that may have tapeworm eggs in it, that not sufficiently cooked, can then maybe infect the vertebrate host, or here. Okay? This is an image of a tapeworm. One tapeworm, rather long. They attach within the GI tract of the host, and when we think about evolution, a lot of times people think, oh, these things aren't very evolved. They've lost their digestive system. They don't need one. So the ancestral forms of this group, if you look evolutionarily, before we had the three groups, the ancestral forms all had a GI tract. But the cestodes were able to lose it because they're in the nutrient-rich environment of the host, right? Also, if you think about it, since these two groups are parasitic, they have to have some ways to evade the immune system of the host, whether it's the vertebrate or the invertebrate. So in fact, the feature that distinguishes this from the free-living ones is a specialized surface called the integument. And that helps them to overcome the immune system of the host, whether it's the invertebrate host or the vertebrate. Invertebrates do indeed have immune systems. They have defense systems. They're not well studied. Clearly, a lot's going to be learned by them. So if you look at this tapeworm here, they have this scolex here, basically how they attach. They attach to the wall of the GI tract. Some people say they can feel them right around in their GI tract when they're infected. Clearly, it's an issue with anemia, uptake of nutrients, etc. And the medicine that they give to get rid of these affects the scolex, these hooks, and the ability to stay attached. And if they lose the attachment, then the individual just basically defecates out the tapeworms. And it takes a while. Okay. Hang on. How many of you have heard the ads about the lap band? I drive down LA and you go by all these things. Lap band, lose 8 inches in 30 minutes, etc., etc. Well, that kind of advertising has always existed. And this is what an ad used to be for a diet pill, which was tapeworm eggs. There's been lots of things within the last 10, 15 years that have been used for diets and damage heart valves, etc. So you always have to be careful about the diet medicines. Anyway, eat, and always stay thin. Well, that's probably true if you have lots of tapeworms. I like this. No diet. How many of us want to just take and go have that tea and then we'll lose 40 pounds, right? Be nice. Anyway, no baths, because people didn't just like to bath. No exercise, yeah. I love this one. No ill effects. Friends for a fair form. Yeah, right. Anyway, moving on to the free-living ones. This is the one you'll look at in lab. This is the free-living one. There's those eye spots, not image-forming. So you want to look at that with the microscope. Here just shows you the digestive system. This is a gastrovascular cavity. One opening, mouth/anus. Okay, now, I'm going to point out to you the naming here. I would never ask you this on the lab exam because I think it's too confusing. But the mouth here is the opening into this cavity called the pharyngeal cavity. It is not a coelom. It's a cavity. And that pharyngeal cavity allows the pharynx to be everted out the body, and then this would attach to food. So when you have you feed it some egg whites, so for the platyhelminthes, there's going to be demos. There's going to be feeding and slides. Okay? So we're going to just have you take some egg white, and hopefully you'll see that tapeworm evert its pharynx, which is highly mesmerized, which will pull food in. And what that does is as food enters the pharynx, it gets distributed through the cavity. It gets distributed anterior and posterior, and then digestion occurs within that gastrovascular cavity, and then the nutrients simply diffuse outward into the solid packing of cells. Solid packing because it's acoelomate, no coelom. Okay? So the cavity here is not a coelom. What we see here is just that gastrovascular cavity. Here we have some slides where this is in red to see it very easily. Okay? Here we see cephalization. We see the nervous system is basically like a nerve ladder, runs along the two sides, and then increased clumping here associated with the pseudo-eyes there, the eye spots. Question, yeah. Sure, the question is what's the difference between a cavity and a coelom? A coelom is an internal cavity. Okay? So you probably heard the term oral cavity. I can take food in my mouth, I can spit it out. I've never crossed a membrane. I've never been inside the body of the organism. Now, if I want to get in my abdominal cavity, which is the true coelom, I have to cross cell membranes, okay? So cavities are open to the outside. You don't necessarily have to cross a cell membrane. Now, cavity is a general term for a space. Coelom is a specific term for a space that's within the organism, okay? So, all right. It just shows you in terms of the nitrogenous waste here. So it shows you that there's repetition through here, so that's some of the metamerism that we talked about. One part of this is called the flame bulb, and notice what they do. Here it just shows this flame bulb, and then it leads, there's this tube, and there's an opening outside here on the body wall. So this is what I talked about last time. Once the fluid gets pulled in here because of the flagella bead, once the fluid's inside this tube, it's effectively outside the body, so things can be selectively absorbed back in or selectively secreted into, so it gets secreted out the body surface. So on this flatworm here, there are many pores here where those wastes are emitted. Now, since these are in the aqueous environment, the nitrogenous form is ammonia, and that mostly just diffuses across the skin. But in terms of osmotic balance, that's what the role of these tubes are. It's for osmotic balance, okay? Any questions? Again, it's a common concept here that once it enters the tube, it's effectively outside the body. Then this just shows you the repetition of the testes and the ovary here. And they do have sexual reproduction and asexual. This is a cross-section here. Now let's just go from the outside body wall here to the gastrovascular cavity. Remember, it's been cut. So on this, and I apologize if this gets a little complicated, but you always have to think back to the organism. So let's go back here. If I make a cross-section through here in various places, you can expect the cross-section would look different, right? So on your prepared slide, there are multiple cross-sections. Always look for the cross-section on your slide that matches the figure in the lab manual, okay? Because there are multiple cross-sections. So if we had something like here, you could see if we did a cross-section here, we would get the pharynx in that cross-section. If we did a cross-section down here, we would no longer have the pharyngeal cavity of the pharynx, so we wouldn't see that. We would see the branches of the gastrovascular cavity, though, right? If we were anterior, we'd see just one branch. So you could actually figure out from the slide if you were anterior of this cavity or posterior. So if you're anterior, if it's far enough, it'd be just one. If it's posterior, it's two. So when we get the cross-section here, again, trying to stress there are multiple cross-sections on the slide. So here would be where we have the gastrovascular cavity branch. There's that gut there. So let's look at this here. So here we see the pharyngeal cavity. That allows the pharynx, here, this entire structure of the pharynx, to go in and out of the body. Okay? That was illustrated in this figure here. So we had the pharynx pulled within when we did the cross-section. So the pharynx is in this cavity. So when we look at cross-section like this, there's a pharyngeal cavity. That is not a lumen. I mean, sorry, it's not a coelom. There is an internal part of this gastrovascular cavity called the lumen. We usually call the interior of a tube a lumen, or like the thylakoid and lumen of a chloroplast, etc. So this is the lumen of that gastrovascular cavity. Is it branched anterior, one branch, and posterior two? So we see those two branches, okay? But notice a solid packing of cells here, and there are muscles here that connect the two surfaces, because when these locomote, they need to be able to control muscles on that, and they do have cilia on the ventral surface. These are bilaterally symmetrical, so we can talk about the ventral and dorsal surface. So they have cilia on the ventral surface, this side of the board, the back side, for moving. This is the dorsal, okay? The slide will look something like this. So here's that large pharynx. There's the pharyngeal cavity. There's the two branches of the gastrovascular cavity. There's its solid packing cells. Okay? And you can't tell this very well, but if you look with your microscope, you'll see this side looks a little fuzzy compared to that side, and that fuzziness is due to the cilia. But it's not real clear there, okay? Any questions about the polyhelminthes? All right, so let's talk a little bit about the annelids then. And we have three classes here, the oligochaetes, polychaetes, and hyoidinia. These are easy. Oligo means few chaetae. Polychaetes mean many, and hyoidinia is a completely different name. These are the leeches, and we'll do a feeding demonstration in lab. So what we'll do is we'll fill up some, basically, if you eat natural sausages, that's meat that's stuffed into intestines, basically. That's the casing. When they say natural casing, that's intestines. So what we'll do is we get some intestines like this, and we fill it with typically cow's blood, and then we'll tie it off, and we put it in a little aquarium with the leeches, and they'll feed on it. And you'll see the leeches get really large. Okay? We've had students offer to do leech feeding demos on them for extra credit. We don't do it. By the way, the ones we use are medicinal leeches, so they use these after surgery, and they may attach them. For example, we have some images in the lab from the supplier of these leeches. For example, if you cut the lobe of your ear off or things like that, reattach it, you tend to get very poor circulation there. You tend to get clotting and things like that. So what happens is by attaching leeches there, it increases blood flow, it will scavenge the dead tissue, et cetera, et cetera. So leeches were used a long time ago in surgery, and they're definitely going to come back in terms of recovery. All right. So I know one time I was in Yosemite swimming in the stream, and I got out and I had about, I don't know, 300 leeches on me, and we quickly took them off. If you need to, they just pour some salt on them. They come right off. Okay. Anyway, finally here we have three germ layers, just like before. So now we have a branch here of the annelida, okay? And I'm not going to go over this chart here. This just shows you an earthworm on the surface. You'll oftentimes find them on the surface after a heavy rain. They have a closed circulatory system. That means they have blood. This is a closed circulatory system, so we use the term blood. So there's a heart. It's actually called a pseudoheart. You'll see that in the dissection. But what happens is they live in the soil. There's spaces between the soil, air pockets, things like that. When it rains heavy, those air pockets get filled with water, and they basically can't get enough gas exchange, so they come up to the surface to basically prevent from drowning. Okay? So that's what happens with heavy rain. They also can come up to the surface because it's easier to find a mate on the surface than there is in a large volume of soil, because this is just one surface area, one plane here. So as the earthworms come out, they're all with this one plane. If they're in a column of soil, it's hard to find. Okay? Also more difficult to mate in that column of soil. So here just shows you this. There's a structure here. You see many rings here, segments. Okay? So these are sometimes called the segmented worms. This is the clitellum here. These are called monoecious, meaning they have one house for both gonads. Sometimes people use the term hermaphrodites. But they have both ovaries and testes here. So the way they do this, mate, is basically two earthworms will align their clitellums. They have mucus glands here. They secrete mucus. And you'll see this actually on the earthworm if you look carefully. I don't have an image of this, but this is the earthworm that you'll be dissecting. Basically, we put them in ethanol, and that's what kills them. And on the ventral surface, they are bilaterally symmetrical. On the ventral surface, if you look carefully, there's some little lines. So when these things line up like this and glue the clitellums, they make a groove, and it's called a sperm groove. So one earthworm, it1, mates with it2. It1 releases sperm, it2 takes them up, it2 releases sperm, it1 takes them up, okay? And then they'll store the sperm in structures called spermatheca, and then eventually release the sperm and fertilize the eggs, okay? So the dissection is very straightforward. You'll want to make one cut laterally with your scissors. Hold the earthworm in your hand. We do have gloves for this, but hold the earthworm in your hand, make one lateral cut. Remember, try not to puncture structure, so do this as least invasive as possible, cut the surface. And then, because you don't want to puncture all the way down, so make a cut, and then lift the scissors and cut anterior, all right? And then what you do is pin the worm off to the side. This just kind of shows you what it'll look like in an ideal diagram here. Here's the blood vessels. There are arteries on the top and bottom, and they have rings of the vessels that go around the circumference, connect the dorsal to the ventral. So there's what's called a dorsal blood vessel and a ventral. Dorsal blood vessel here is your landmark. That's how you know this is the dorsal surface. The ventral is also somewhat flattened. So you use the dorsal blood vessel as your landmark. But in the anterior end, about 6 or 7 of these rings beat a lot more. So the entire dorsal blood vessel beats, the entire ventral blood vessel beats, but the rate is slower than here. So these 6 or 7 beat a lot more.